Welcome to qnawire.
We have a system of masses arranged on a square like this, and we want to find what the total force on this small mass at point P is. So we can do this just by looking at each individual mass and finding the force and adding them up. But we can probably do a few tricks to make this a little simpler. So to start, we'll say that the net force on P, first we'll think about this 2 kilogram force, since that's going to be moving directly along this line. And in fact, if we look kind of by symmetry, these two smaller masses, this one pulls up, this one pulls to the right, their net contribution is just going to be along this line as well. So I'm going to indicate the direction of the force right away as being along this direction. So I'll just call that the x direction. So this net force is in the x direction. And so we have the gravitational constant, and then we have times mass p. And now let's start with the 2 kilogram mass. So that's pulling up along this line, so we've called this the positive x direction. And so we have its mass of 2 kilograms. And now we need to divide by the distance squared. So this square is half a meter on each side. So we could do Pythagorean's theorem to see pretty easily that this long horizontal distance then should just be root 2 over 2. So we're just doing 0.5 squared plus 0.5 squared, the square root of that. So we have root 2 over 2, that whole thing squared. And now we can add on the other forces. So again, this mass is pulling this way, this one pulls up. Their net contribution is going to be just along this line. And so we can get that, it looks like then, by taking their full force in the horizontal or vertical direction and then doing cosine of 45. So I've drawn in this line here. So here we have what the full force is. We only want to know the component along this direction. So we can do cosine to get adjacent this term over hypotenuse, the full value of the force. And by symmetry, it'll be the same thing for this. So I'm going to say that we have 2 of these terms. So 2, and these masses are 1 kilogram. And then the distance is 0.5 meters squared. And then we have that cosine of 45 term. And so now we should be able to evaluate that, and we'll get 9.67 times 10 to the minus 12 newtons. So now part B asks us if we place this mass at point P 300 meters away along the same line the force was directed, what would its velocity be when it reaches this point? So we'll go on a new page for that. And because these forces are so small, and then we're going 300 meters away, we can pretty much approximate that potential as just being 0. We could put in actual numbers for it, but it's such a small effect, it won't make a difference in the final velocity. So we can do this with just conservation of energy. We want to say that the initial energy, so this is the initial where the mass is put 300 meters away and is at rest, should equal the final energy, so where it's now at its original point P. So the initial energy, we have kinetic plus potential, and that should equal the final kinetic plus the final potential. So the initial kinetic is 0 because it's at rest. And then we've said that this initial potential is very, very close to 0, so we can just approximate as that. And so then we can find that the final kinetic energy should just equal negative final potential. So that is 1/2 mv squared, and this is mp, the mass that we're interested in. And that equals negative u final. And we want to find what v is, so we'll just solve for that. V should equal then, bring over the 2 and divide by m, so 2 over mp times negative u final. And this whole thing will be under a square root. And that's multiplied by. So we can evaluate that a little bit more. So we'll have 2 over mp And then our final potential energy, we can go back and look at our diagram here. So now all we care about is just the distance from each of these masses. So the potential between mass P and this 2 kilogram one will just be associated with this distance, the other ones with just these vertical and horizontal distances. So starting with the 2 kilogram mass then, we will have, first we'll have gravitational constant times mass P. And this whole thing has a negative sign, but then because of this negative sign here, it ends up being positive. So we have gravitational constant times our mass, and now times the 2 kilogram mass to get its potential, and then divided by its distance, which we said was root 2 over 2. And then we have two 1 kilogram masses. So I'll do 2 times 1 kilogram because they're each the same distance away, so we can group those terms. And they are 0.5 meters away. So one thing to note here is that these masses cancel out. This is all under the square root. So its final velocity doesn't depend on its mass at all. No matter what it is, it'll end up with the same speed. So this is very similar to things on Earth when they fall from a height. It doesn't matter what its mass is, assuming there's no air resistance or things like that. It's always going to end up with the same velocity. So this is about as simple as we can get this, unfortunately. So it's a bit of a big expression, but without these masses, we just kind of have a bunch of numbers in here. And so we can evaluate that, and we should get 3.02 times 10 to the minus fifth meters per second. So very slow. Gravity is a very weak force. And you can check if you did actually put in what this initial potential energy term that we ignored is, this answer wouldn't change at all to this precision. So that was a pretty reasonable assumption to make.